first part, A, is burst of localized states for set, and the second part is measuring the amplitude equations. So, here you have this kind of stability diagram. It's actually a bifurcation diagram, and now we are going to see how these systems behave apart from this saturation value. One way to observe the evolution of an amplitude rather easily is if you don't have a forest, I mean a sample of trees. It's always difficult to look at the height of the trees in the middle of a forest. And as I told you, we have this X-ray system to do that. But of course you can also look at a single tree on a plane. And it's not so clear that this can be done, but there are systems like in granular matter or in mud where you can observe not only extended full patterns, but also isolated objects, like in granular matter. This is just some steel beads vibrating from below. You have these oscillons, so these are localized states here, or you have these clay solitons. So this has been very well known. The question was, does this exist also for the case of the Rosenzweig patterns? The Rosenzweig patterns, as I have shown you, are very well known since 1967. So we thought about what is it possible to generate a localized state of such a Rosenzweig pattern. And to do so, we tuned the susceptibility. Before I've shown you a liquid with a susceptibility of 1.1 initial susceptibility, and now I choose one around 3, and there are actually no real calculations but some estimates that the hysteresis should scale proportional to the square of the susceptibility. So if you are increasing from 1.1 to 3, the square of 3 is quite a lot. It's 9. And here you see such a hysteresis. These are once again measurements, green for upgoing, and blue is for downgoing, well, that is too fast for downgoing field. And you see that we have here a rather huge hysteresis of 1 millitesla, and you see also that the solutions of the amplitude equations, this blue and red dashed curve, the parabola, fits nicely the experimental data. So this is a fit. So this shape in principle is a prediction, but the prefactors have not been predicted here. This is not a finite size, finite element calculation. So anyhow, you see now that we have a large subcritical bifurcation. Subcritical means that you have here a hysteresis, and that this branch here is unstable. And now the question is, what will happen if we disturb the system? Here you have the flat layer here, and you see that you have a B stability. Here you have the extended pattern. And now the question is, what will happen if we disturb the system somewhere in the flat layer, where it's already B stable? And this we have done, and for reasons of reproducibility and well-defined parameters, we applied here a small additional probe coil beneath this dish, and now I switched on this additional field in this B-stable regime, and you see a solitary spike is popping up. Well, this is not remarkable. Remarkable is that if I switch off the additional field, it remains. It does not go away, does not collapse. But also what is remarkable is that this perturbation does not propagate. Usually, if you have oversaturated salt solution and you put in something, you have a crystallization and the front is propagating. Or you have an undercooled liquid and you put in a nucleus, the front is propagating. Here, it is not. And this is outstanding. So here once again you have this guy. And why is that so? Well, here you see some height lines of a regular standard pattern from the X-rays, and you see that we make a curve profile from one peak to another. This is this blue line here. And the red line is a cross-section from something we call a ferrosoliton or localized spike. And you see that these profiles are very similar to each other. And there has been a prediction, or actually a conjecture more or less, by Moore. And he said in an article in 1986 that if you have a periodic system, I mean a system which is producing a periodic pattern, then so if you make a perturbation, this wavefront should not move continuously, but should be modified by the periodicity of the pattern itself. This is like you're going on an old railway track where they have these tracks which are finishing at some point, and then you have the new track. If you hear at the noise, always going bom 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 bom. Yeah. So it's here also the wavefront should go bom 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 bom. So and then he says in a small side sentence, it might be also said if KBT is slow, there could be a case where this wavefront can get stuck. And this is exactly what we have, because our system is a macroscopic system. The spikes have a diameter of 1 centimeter or so, or the wavelength is about 1 centimeter. So these are huge energies compared to KBT, and so our wavefront cannot propagate. There is not an energy anymore to shift or nucleate the new line of spikes. And that's why this kind of ferrosolitons are existing in some machine stable here. And you see that their amplitude is slightly larger than the standard pattern amplitude. That is because such an object sucks up more liquid when it's going, there's no competition. And you see that it's also more or less limited to the bistable regime here. Now, certainly, when I observed that, I asked some people in numerics, couldn't you try to find these guys as well in some simulations? And there was Olga Lavova at the University of Magdeburg, and it took her a long time, probably some similar problems, what you mentioned with this initial situation, to nucleate a small bump or crest, which then eventually evolves into a stable localized state of the ferrosoliton. And here you see such an object. So, and please don't look at the black lines, just look at the red solutions, because the red solutions are calculated for a three-dimensional pattern. Here you have the standard Rosenzweig instability, and here you have this branch which describes the localized state. Now, you can, of course, make more analysis on these static patterns, but I already announced that we would like to have a look on the gross behavior of such an object as well. And this can be done because there are no other spikes in the way anymore. And this you see now here. I am now increasing the local magnetic field in the center, and you see that here a localized spike is popping up. It's growing and it's growing. Of course, this is a fast camera taking 1,000 pictures per second. And here you see the amplitude is plotted. And now if you apply a smaller local probe field, it takes a bit longer, and eventually it takes much longer and much longer. And this we didn't understood in the beginning. We couldn't understand. But then of course you are applying less, even less fields. You eventually end up at a critical field where no localized state is popping up anymore. And I try to describe now our current understanding of the situation. Here you have the homogeneous pattern, and for a certain field, homogeneous field applied, you can add such an additional field, and you can do that here as well, and so on. And you can ask what is critical induction of this additional field, of this probe field, P, as a function of the overall Helmholtz coil field. And this we have done as well. And this is the outcome. So you see that here you have the induction of the probe coil, and it's almost going linearly as a function of the Helmholtz field. And then at the critical Helmholtz field, of course, then you have a spontaneous formation of spikes of the standard Rosenzweig instability. It's going zero here. Okay, this is the observation, but let's try to understand that now. And well, we write down an amplitude equation. This is the standard amplitude equations for the subcritical instability. Now we have to take into account this local field. This local field is not homogeneous, and because of that, it's creating a kind of imperfection. And an imperfection in such an amplitude equation is well described by some additional term B and some additional parameter epsilon 2. Epsilon 1 is here the standard, somehow the standard Helmholtz field, and here this is the probe field. So now I am increasing this imperfection parameter, and I show you what is the result. You see that here this corner is a bit smeared out. Now we have 0.2 millitesla. So we are increasing to 0.3 millitesla, 0.4 millitesla. And here is where our system is at the moment. We have a Helmholtz field of 8.9 millitesla. You see that we are still sitting quite stable here. It's a flat surface. And now I'm making a switch to a larger probe field, and a larger probe field, and a larger probe field, and you see how this additional term, this imperfection, is changing the solution curve. And eventually you see what's going on, that here this crossover, I mean this is increasing. And now if I increase furthermore my probe field, you get here a curve where you don't have any crossover with this line here. So this position is getting unstable, and where is it? And this spike is going until you have the final state. Now the question is, how long does it take to grow? And you see that if I'm increasing further, this distance here is getting larger. And this is something, this goes over here, and then this detachment, this is something which is described by a 7-node bifurcation. And for such a cell node bifurcation, it's very well known that with increasing distance here, this growth should increase in a specific manner. And this is what the experiment is showing you. You have here the increase of the amplitude, and then for a long time you hardly observe anything, and then you have this shooting out. And this is what you get from the simulations of this simple amplitude equation. You see that for a long time you have hardly any increase, and then you have this shooting out. So this is very characteristic for a cell node bifurcation. And it is also well known that for the scaling for this time which takes you to overcome here this regime where you have little growth, this delay time should scale 1 over the control parameter epsilon probe, and 1 over the square root of epsilon probe, and this is here's distance, and this is what we found. So you see here now, this is the predicted scaling, and then now I square this tau delay, and by squaring and taking to the -2, actually something which is proportional to this epsilon p should be observable. So you get some kind of linear dependency of tau or t to the -2 versus this epsilon parameter. And this fits very well as an experiment. So you see there is just a linear proportionality. This kind of cell node bifurcations are very well known from a lot of different fields, like jet lag, for example, or other systems. Now we have a look at the phase diagram. I've shown you that we can measure the critical induction of the probe coil, which is necessary to initiate such a ferrosoliton, and this we can also get out of this model. You see these are these orange dots where for a specific Helmholtz field the situation is getting unstable. Now we plot this local critical field as a function of the Helmholtz field, and what you find here is that this model and the measurement are nicely working out. Of course, we have here 1 or 2 fit parameters. This is not a quantitative agreement, but you see that the qualitative model is describing very well this transition. Here you have a small disturbed surface. This is the case, well, let's go back. This is the case, what we have here. This small disturbed surface is the case, let me say, here. Yeah? You have here a crossover. You have here a small bump. That's exactly the bump before it's getting unstable, before it's popping up. This is this point. So, here we are. So, this mission is accomplished, the birth of a localized state. Now, once you are able to measure the birth and development of a localized state, you're getting more eager, and you say, well, why we shouldn't be able to measure the whole pattern as a evolution, during its evolution. And as I've shown you with this thin liquid, this is not possible because of technical reasons. You have a limited amount of X-rays and intensity, and this system is popping up very fast, within 80 milliseconds or so. So you don't make one X-ray picture, and then you are done already. We are able to make 7 pictures X-ray pictures per second, 7 frames per second. So this is not so fast. And this is just because these detectors are lazy. And also, if you have faster detectors, you need much more intensity. So what we can do is, I'll show you very soon, but one motivation for this going into this temporal evolution of this full pattern is that there are two kind of predictions for the amplitude equation for the Rosenzweig instability. These guys, Stefan Bolius, Harald Planger and Helmut Brandt, they have here this kind of amplitude equation. This is the temporal evolution of the amplitude, and these are some prefactors, and a to the square, and a to the third power. Then you have also this model where you see that in addition to this beta, you get here some epsilon dependent prefactor. And now we said, okay, what is the proper way? What is the most efficient way to describe that? This is not really a contradiction, it's just that this is a more elaborate description. And so this gave us the idea to measure the amplitude equation directly. That means you measure the temporal evolution of the amplitude. And this can be done if you jump into some position of the parameter space here, and then of course the system will move towards its stable branch here. So you measure the amplitude, and after some time you measure the evolution of the amplitude. So you can directly measure the evolution of the amplitude, but this works only if the evolution of the amplitude is much smaller than the change in your control parameter. If it takes you a few minutes or a few seconds to change the magnetic induction, you cannot really independently measure that. And here, as I mentioned before, with the standard liquids, we have a viscosity in the range of 5 millipascal seconds. With a carrier liquid like kerosene, this is not possible. But then we thought, okay, let's take a really viscous ferrofluid. This is something which I show you here. So this is really a syrup. This is honey, more or less. So now we are much better off because the system is much slower, but still it's not slow enough. Of course, you can go to the chemists and ask them a long time to do this proper way, but also you can, as a physicist, you can say, well, hey, we just cool the system and we cool it down to -5 degrees, and then it has already 18 Pascal seconds, and if you want we can go even lower. And in this way we get a Rosenzweig instability. So you can really force down the time scales in a way that it fits to your detector. This has been done by Christian Gollwitzer during his PhD thesis. This is a setup where you have on all 8 sides a Peltier cooler, which is then connected to a water bath, and you fill here the ferrofluid in. Here you have one Helmholtz core, the other one is underneath the side. Then you have these Peltier elements to equilibrate the system at the desired temperature. And, well, for obvious reasons, you can call it an octopussy. And now I show you what can be done with such a setup. So, you might, in the beginning, jump to an overcritical field. Now the zero realizes, oh, I have to go. This is what's going on now. Here you see some real time, well, it's not real time, it's by a factor 3 or so faster. So this takes in real time about 3 minutes for the pattern to go up. This is now a measurement with the X-rays, and you see that these spikes are really going and going and going. And you see also some flicker. This is the noise from the photons. And eventually you have this pattern. So, I don't want to have this again. And now you jump at some other parameter, and then this pattern should relax from above. And it does. So you get here the evolution of the amplitude, but now you are jumping here in this regime 1. So you want also to go into this regime maybe 3 in the inner regime. How this can be done? Well, you can jump up, then you jump relax, and now you jump back into this regime. And as a consequence, you observe such a relaxation of your pattern. So nice, that works. But you also might want to go into the regime 4, where the pattern should decay to 0 once again. You go up, you go down, and then you wait a little longer, and then you jump into this range, and this is what is expected, and this is what you observe. Now, this has been done not only for 3 values, but for 205 seeds in the phase space, recording altogether about 170,000 X-ray frames, and that is the outcome. All these red points are the data, and then you have a color code. Red area means a going amplitude, going pattern here. Then blue means a shrinking pattern here, and green means the root of the amplitude equation. That is here not so much dynamics is evolving. So you see this green range is nicely grouped around this curve. Now once we have that, we check how the predictions fit to the experimental data. So for a nice description of the experimental data, we use a radial basis function network. This is just a technique to get some smooth curve out of all this data here. So this black curve is this kind of network, and now we compare this black curve, which is the essence of the experimental data, with these 2 amplitude equations. Now I flicker in between this solution of the 2 amplitude equations, and you see that this blue equation much better fits here the hysteresis with this additional prefactor. Okay. Now, why we have here some voids? These voids are actually the main message. So far, this can be understood, but what's happening with the voids? Well, I show you what's going on with the voids. Here on the left-hand side you see the evolution of the amplitude, and on the right-hand side you see Christian's measurement of the pattern. Now you jump down and we jump back. Now the pattern should decay, but what is taking place? It doesn't want to decay, but it is not developing a homogeneous pattern, but it is developing a localized state. these guys, which we have created before intentionally by some local distribution, they are now somehow going up by themselves without an external perturbation. And this is something which makes you think. You see, it stays here for a long time. So why these guys are existing here in these voids? So this is where we observe this localized state. Well, this is now a very active research area. It's a special regime here where something which is called homoclinic snaking is taking place. Homoclinic snaking is a very strange form of bifurcation diagram or bifurcation range. And you see that here in this regime there should be a lot of different patterns of localized states, or not patterns, but localized states should be stable. This is a prediction, and this is what we found. So in this regime, where the voids are, you find a lot of different localized states, like 3, 4, 5, 6, like the numbers on a cubicle. And this is now something where we are very much interested to explore the range of existence of these localized states. And there are some calculations on this homoclinic snaking, for example by David Lloyd. And you see that here, if you wander on this homoclinic snaking curve, you can create larger and larger localized states here. And of course it would be a dream to some extent to reproduce that in the experiment. It's not so easy, but with the zero liquid we have the possibility to be successful. So this is time for a short conclusion. So we have seen in this field of pattern formation that the wave number of maximal growth is linearly increasing with some kind of induction. Then we have seen that the maximal growth rate is behaving according to some scaling law. We had a look on the shape of the patterns of a profile. We had a look at the hexagon square transition. Then we investigated some horizontal, the impact of a horizontal field component, and then eventually we went over to localized states and had a look on the growth rate and the scaling of these localized states, and in the last parts we were dealing with the growth rate of the fully developed pattern, and Noland Woland found out that this is still related with localized states as well. And this research has been conducted within the priority program. In German it's called Schwerpunktprogramm 1104, and within the research group 508. So this is, thanks a lot for your endurance during the morning and this afternoon. And here you see part of our people, which of course as usual did the main work. So this is a delayed conclusion.
Some questions for this part?
And it makes no difference. No, its impact is on the square of the magnetic induction, so it doesn't take care about if where is the north or the south pole. This is not important because this is super paramagnetic. So they are immediately orienting in the direction of the field. So that's yeah, this is always, with magnetic fields, usually always proportional to the square. Of course, it would be, in other systems it makes an effect, but here it does not make an effect.
You always brought in the original axis, the B field.
Yes.
You don't put H.
Well, right. Well, H is, it's not a real field. Well, no. What we measure is B, but of course, B is a magnetic induction, and H is a help field, in a way. You know? Of course, you can also calculate one into each other. You have just to say what is what. And here we are measuring the magnetic induction with a sensor mounted immediately beyond the vessel. So this is what we measure. Of course,
in the brackets
of the ferrofluid. Yes, yes, yes. Of course, well, this, if the liquid layer is extended, it makes not a big difference because a deep magnetization factor of a shallow layer of ferrofluid is almost 1. So, no, almost 0. Well, I'm getting confused over this. So it has hardly any influence. It's getting very important if you put in such thing, for example. This attracts a lot of your flux and then changes the whole field configuration. So it's very important to have a highly extended layer to get an as homogeneous as possible field, or correctly it's induction, magnetic induction. But I remember that already when Maxwell died, there was a lot of controversy whether to use H or B, and you can do both as long as you say what you are doing. Pardon?
Maybe we can just move on to the next topic.
Yes, of course. So the next topic is flow in ferrofluids. Well, so I was at this nice cafeteria or mensa or whatever restaurant, and I had lunch and I enjoyed this food very much, and I had a salad and these tiny eggs. So who of you have had such a tiny egg? Nobody? Nobody was eating such an egg? No, it's well done. Well, in the following I want to show you the connection between these eggs, or any kind of egg, and flow in ferrofluids. What is dangerous? Oh, really? So let's have a look. Here you see a flow pattern. So red means high flow velocity, blue means low flowing velocity. This is a flow pattern in a square cross-section of a channel. And it has been here on some cover recently, and I want to use it as a title for flow in ferrofluids. The flow in ferrofluids part is made up from 4 chapters. And the introduction, well, I already had into ferrofluids, but then I would say a few words about static fields, the impact on static fields on a Purcell flow, pipe flow, then the impact on an alternating field of such a flow. We move on to the impact of a rotating field onto ferrofluidic flow, and eventually we finish with consequences of periodic sinusoidal magnetic field or induction, which is traveling. So this is a lot of program, and probably I'm finished in 5 minutes. So let's keep this main topic for tomorrow. I mean, I think it's more important to go into slow speed, into detail, than to put too much facts into your brain. Anyway, it's a very tough course here. So for today I will just stick to point 1, which is more of the introductory part. You have here a flow in a pipe, and as you might know, in such a pipe you have a parabolic flow profile. So in the middle you have hardly any friction, so here you have high velocity, and at the edges the liquid sticks to the wall, and you have velocity 0. Now what's going on if you have magnetic particles in here? Well, as long as you don't have any magnetic field, they are just rotating, because here on this side the velocity is higher than here, and so you get rotation in the flow, and this creates some vortices or some vorticity, and so the particles have to rotate. Now we apply constant and hopefully homogeneous magnetic induction or magnetic field, and what will be the outcome of that? Well, this experiment has been performed way back in time by Mr. McTagg in 1969. And you see here something, it's called reduced viscosity, plotted across the Langevin parameter alpha. Well, this you know already, this is dipole moment times the outer magnetic field. Now you see that this reduced viscosity is defined as the viscosity change due to the magnetic field. So this is the viscosity before minus the viscosity with magnetic induction divided over the viscosity without any field. So this reduced viscosity is increasing. That means that you are, by this constant magnetic field, you are hindering the free rotation of the particles, and this increases the resistance between neighboring layers of the liquid. And the nice thing is that you can describe such an effect as long as your liquid is diluted by a rather simple formula, where 3/2 times this is the hydrodynamic volume fraction, and then this is alpha. We know already the Langevin parameter, and this is the square of the Langevin function, and this is alpha minus the Langevin function. So this has been derived by Mark Schliermis in 1972. Well, some scientist, Mark McTagg, was not just some scientist, but he became the scientific advisor of the President of the United States, Ronald Reagan. This is just a political side remark. So, and I think this is where we finish, and we will continue tomorrow with the story why this flow is connected to an egg. And this is the flow not longer in a static field, but in an alternating or oscillating magnetic field. So I thank you for this, for your attention.
Some questions for this part already? Not only tubes like this, but
permanent plates? No, we didn't do that. But I think there was some work done. But there could be some more work on that. Yeah, I know another group which is working now with square channel. Yeah, and that makes a difference, of course. And well, of course, well, the impact of the static field is something where you can still do a lot of work. But is also a bit boring to some part. So we did not continue here. But there comes in some interesting questions when you take into account particle interactions. Then if there are chains of magnetic particles are forming, then everything is getting very complex and you end up in rheology. And then this is very interesting. And yeah. Co-ed geometry is well described. Yeah. With yeah, I think so.
Questions? So let's thank both these speakers again.